In this unit, we're going to be discussing more of a modern model of the atom. So we left off previously with the Rutherford model of the atom, and we're going to work our way forward to something that is much more consistent with observational evidence. And we're going to be using the Bohr model a lot. There's another model called the quantum mechanical model, which is much more recent. We're not going to get into that because the math for that is really, really crunchy. Right, but to start off with, what we need to talk about is we need to talk about electrons, and to talk about electrons, we have to start by talking about waves and light. You are going to need something to write with and something to write on. Once you have all those ready, let's go. Now, most of you, I'm sure, are familiar with what waves are, right? You have waves in the ocean, those little disturbances in the water that form ripples. That's kind of how a wave works. A wave is a disturbance in a medium that travels through at a regular interval. So, for example, a sound waves disturb the air and they travel through at regular intervals. The note middle C, for example, has what's called a frequency of 256 hertz. That means that 256 waves of middle C will pass through a point in a given second. Okay, so wave is just a regular disturbance, and there are three measurements for a wave that we really care about. We care about wavelength, which is how long a wave is, so the distance between the peak of one wave and the peak of the next wave. We care about the frequency, which is how many waves pass through a point in a second. And we care about the speed of a wave. The speed of a wave is just the frequency of the wave times its wavelength. Right, so I gave you the variables there. The variable for wavelength is the Greek letter lambda. The variable for frequency is the Greek letter mu. Sometimes people will write v for that. And the variable for speed is just the letter c. We'll get into a more specific type of c in a couple of slides, but for right now, the speed of a wave is just the frequency of the wave times its wavelength. Now, to kind of give you a visual that you can use to help you figure out like frequency and wavelength, what we have here, we have a couple of different types of vehicles, right? We have small cars and then we have 18-wheelers. Now, if you imagine that we have a line right in front of this that all of these vehicles have to pass through. If all of these vehicles are traveling at the same speed, which one are we going to have more of pass through that point after a minute? Are we going to have more cars pass through, or are we going to have more tractor trailers pass through over the course of a minute? Again, assuming it's the same speed. It's obviously going to be the cars, right? Because for every 3 trucks you have 9 cars. Cars have a much smaller wavelength than a truck does, much smaller distance, which means that it has a higher frequency. Frequency and wavelength are inversely proportional. The shorter the wavelength, the higher the frequency. Now, the type of wave that we care about here is we care about what's called an electromagnetic wave, or also what we know as electromagnetic radiation. So electromagnetic, or EM, radiation are particles formed from any wave that is traveling at the speed of light. So the speed of light is 3 times 10 to the 8th meters per second. Any wave that's traveling at that speed is electromagnetic. So you can see that what we have is we start off with very long wavelength waves, like radio waves, the things that you actually get through your car. Right, and then we move forward, we go up to microwaves, and then we have infrared, so those infrared lamps that you see. And then we have this tiny little band in the center, which are all the visible colors that you see. They're all electromagnetic radiation. And then we go up to even shorter wavelengths, which give us ultraviolet and X-ray and gamma ray. Right, and notice, the shorter the wavelength, the higher the frequency. Right, so all of these are different types of electromagnetic radiation. They are all traveling at the exact same speed. The one thing about them that's different is the amount of energy that they have. So the energy of electromagnetic radiation, or what we call a photon, which is a particle of electromagnetic radiation. So if you've ever seen Star Trek and they say fire the photon torpedo, they're firing particles of light at the enemy. All right, the way that we measure, though, the energy of a photon of light is we measure it with this equation right here. The energy of the photon is equal to a constant called Planck's constant, which is below, times the frequency. The higher the frequency, the higher the energy. So short wavelength, high frequency, high energy. So these are the equations that we're going to be working with to start off with light. And you'll be calculating energies of photons, wavelengths of photons, and we'll be comparing them to colors. Because remember, the color of light is dependent on its wavelength. Alright, so that is it for this video. In the next video, what we're going to do is we're going to pick up how light was used to get to our more modern models of the atom, which you guys are familiar with as the Bohr model.